water is ever present. In the air and in the ground. And in most industrial processes. And of course, in the sea. Now, steel is the metal most commonly used in engineering. But in contact with water, corrosion becomes almost inevitable. Rusting will damage steel and eventually destroy it. But corrosion can be delayed in many different ways, often by changing the environment of the metal. After returning from a low-level patrol over the sea, dry air is blown through the jet engine until it flies again, and corrosion from the moisture and salt is avoided. Because without water, corrosion won't occur. Many ships and structures which are immersed in water are protected not only by paint, but by anodes welded to the metal which change the environment electrochemically. This effect can be shown experimentally. If an iron rod is left in tap water, it corrodes and produces rust. If it is connected to copper, it corrodes more rapidly. However, when connected to zinc, it does not corrode at all. An explanation begins by measuring the differences in potential. 3 steel rods are in tap water. One is connected to copper and one to zinc. And the other one is used to compare the potentials and connected to a voltmeter. When the steel-copper couple, which we've seen corrodes the steel rapidly, is compared with steel on its own, the potential of the couple is more positive. Conversely, when the steel-zinc couple is compared to the steel on its own, this potential is more negative, and the steel in the couple does not corrode. In the couple, steel is the cathode and zinc is the anode. The steel is protected cathodically. There is a relationship between potential and corrosion rate, and in practice, the potentials are all compared to a reference electrode, in this case, copper-copper sulfate. When this is used with a voltmeter, the same changes are shown. Why these changes occur can be explained in the following way. When metal corrodes, it forms ions and electrons. This is an anodic reaction. For example, when steel is placed in water, it will corrode. The electrons accumulate in the metal, the potential goes negative, and the positive ions find it more difficult to escape, and the process stops. If some of the electrons are allowed to flow away, the metal becomes more positive. The positive metal ions escape more easily, and corrosion continues. Conversely, if we force more electrons into the metal by connecting to a battery, for example, then the rate of corrosion and the rate of producing electrons slows down. As this potential becomes more negative, the corrosion rate and the current diminish. As we have seen, by extracting electrons from the metal, the potential becomes more positive, and the rate of corrosion and the rate of producing electrons, that is the current, increases. When the corrosion product is visible, as the potential becomes more positive, the corrosion rate and the current increase visibly. This measures the anodic reaction rate. Metals placed in water have a characteristic potential, different for each metal. If we couple together two metals having different potentials, for example, zinc and iron, the electrons are extracted from the negative metal, zinc, and flow to the more positive metal, iron. The zinc is sacrificed and corrodes more rapidly, but the iron is protected. However, attached to copper or any other metal higher in the series, the iron will corrode as the electrons flow from the iron to the more positive copper, which is protected. If the electrons accumulate in the metal, the potential goes more negative, and the anodic reaction eventually stops. For corrosion to proceed, the electrons released by the anodic reaction must be consumed by a cathodic reaction, and this goes faster as the potential is made more negative. When the rates of the anodic and cathodic reactions balance, this defines the corrosion potential and the corrosion rate. The diagram also helps to explain the effect of coupling different metals. When zinc is coupled to iron, the corrosion of the zinc increases and the rate of corrosion of the iron is reduced by lowering the potential. This is cathodic protection. In the sea, damage and wear of the paint allow localized corrosion. So, in addition, steel is often protected cathodically by blocks of zinc, which have to be fixed in good electrical contact. Joints in pipelines lying on the seabed are protected by zinc bracelets. For the best results, anodes of zinc or magnesium are cast in a range of shapes and sizes. To ensure protection in the ground, the anode is connected in good electrical contact with the pipeline, and they will, of course, both be buried. Magnesium is often used because it has a more negative potential than zinc, and is put in a cloth bag surrounded by a highly conductive clay. The potential of the anode is checked using a reference electrode and the pipe connected to a terminal on the surface, so that, years later, inspection will show when the anode needs to be replaced. An alternative to using sacrificial anodes is to apply a current from a DC rectifier. The protection can be controlled by adjusting the current and checking that the correct electrode potential has been achieved. The advantage is that a pipeline can be protected for several kilometers. Here from a distant spire one way to the next village in the other direction. Comparison with a copper-copper sulfate reference electrode confirms that the pipeline is being kept at a sufficiently negative potential. To make certain that the pipe is protected along its entire length, it is possible to walk over the pipeline and at intervals measure the potential against the reference electrode on a pole. For steel to rust, there must be both water and oxygen. But where water is essential, as for heat transfer in central heating systems, rusting is avoided because the initial supply of oxygen in the closed system is quickly used up. And without oxygen, there is no further corrosion. Removing air from water will stop steel rusting, because as the concentration of dissolved oxygen is lowered, the rate of the oxygen reduction is also lowered, and so is the corrosion rate, which becomes very low. If air is excluded from tap water, then iron will remain rust-free indefinitely, even though it's connected to copper. The water in the beaker is air-free, and the steel rod is clean. As air is introduced, the potential of the iron becomes less negative. And in a short time, it corrodes. Rust appears in the water. In a power station, some 25% of maintenance cost is related to corrosion. It's even more essential to remove dissolved oxygen from feed water because of rapid corrosion at the high temperatures. And most of the air is removed by mechanical de-aeration. The final traces of oxygen are taken out by chemical reducing agents, such as hydrazine or sodium sulfite. To prevent corrosion in the boilers, the level of oxygen is continuously monitored, as well as possible contaminants, such as chlorides. But in many situations, oxygen can't be removed economically. Cooling systems are one example. But chemicals added to the engine coolant form a protective layer over the internal steel surfaces and inhibit corrosion. Steel is commonly cleaned in acid to remove scale and rust. But an inhibitor is added to stop the acid attacking the metal. When pickling acids attack steel, hydrogen is evolved. But even a minute amount of inhibitor will slow down corrosion and therefore the production of gas. In the motor car, inhibitors are used to restrict possible corrosion not only in the cooling water, but in hydraulic fluids for brake and clutch systems. And of course, inhibited grease and wax are used to protect against internal body corrosion. There is an enormous range of corrosion inhibitors, and there are international standards of testing to ensure that the inhibitor is stable and that corrosion will be controlled. There's a wide range of metals to be protected by inhibitors in engine lubricating oils. In one test, the metal plates remain in heated emulsion for many hours. They are then examined and the amount of corrosion compared with a standard. Cutting fluids often contain dissolved oxygen and water. An inhibited cutting oil emulsion is tested on steel swarf on a cast iron plate. The resulting corrosion, after a set period, is evaluated. This checks not only the protection of the cutting machine and tools, but also of the manufactured components. In a generating station, the quantity of oil needed to lubricate a turbine is very large. Some steam always leaks into the oil, and most of the condensed water is removed by centrifuging. But inhibitors have to be used in the oil to prevent corrosion of metals from water remaining in the system. Body pressings for cars are manufactured in considerable quantity to maintain a production model for many months. So, during manufacture, the pressings are protected with an inhibited oil and then stored in vast rooms, which need frequent access. Now, where steel is exposed to the atmosphere and oxygen obviously cannot be removed, rusting can be prevented by reducing the humidity and preventing the formation of liquid water. This is achieved by circulating the air through a dehumidifier, and a positive air pressure is maintained in the room. Because it is not necessary to remove all the moisture from the air, corrosion can be controlled economically. Only when the moisture is above 60% relative humidity will steel rust. This has considerable use for interiors, both large and small. Here, engineering components are protected during storage by dry air blown down from the room above. The air drying plant consists of a rotating drum with a drying agent, which removes water passing through it. The drying agent is then regenerated as the drum rotates, and the condensed water is put to waste. Cold water is drawn from the depths of a lake to supply a small town. In the pumping station, this caused considerable condensation on supply pipes, which led to corrosion. But the problem has been overcome by using air drying machines in the corridors. Many very large structures are made up from box sections. The exterior is relatively easy to paint and maintain. However, it is immensely difficult to repaint the interior because of solvent fumes, and indeed very expensive. So here again, the dry air method can be applied successfully and cheaply. Similarly, the suspension cables need protection from corrosion in the anchor chambers. Again, dry air is used. A larger application of dry air was to protect a generating station while out of service. It was to be shut down for a 5-year period, with the ability to restart within 3 months. Incoming air was dried by machines located around the building to keep important components at a relative humidity of about 50%. Steam generating surfaces were protected by dry air, and some pumps, which had been designed to run immersed, were protected by an inhibitor. All these systems were checked every day and preserved in good working condition. Each day, too, the turbine was rotated manually to circulate inhibited lubricant to the moving parts. With the changes in the fuel price, after about 3 years, the plant was put back into service without any serious corrosion problems. Dry air can also be used in a slightly different way for the temporary packaging of machinery in transit. Silica gel packets absorb moisture, and the machine is completely enveloped in plastic. As much air as possible is taken out and the package sealed. This gives protection not only against corrosion from moisture, but from acids in the wood of the packing case. After a fire, damage to machinery and equipment from corrosion comes from the water used to extinguish the flames. So here, an inhibitor is added in the last damping down by the hoses. Drying out is then essential for preservation. The corrosion wagon carries an air drying machine and all the necessary equipment to help prevent rusting. Important items are covered and connected to the dried air. But intensive corrosion will come from the acid formed when the water dissolves the products of combustion of the plastics used in modern building. 1 kilogram of PVC burned in air gives a litre of concentrated hydrochloric acid. So chlorides are estimated by taking a sample and titrating on portable equipment. All chlorides must be removed. The vehicle carries cleaning facilities, and an inhibitor is added to the last wash. Quick drying is then essential, and finally, there's a coating of inhibited oil. By fast and appropriate action after a fire, damaging corrosion can be reduced with considerable savings in cost. Rusting will destroy steel, but it can be prevented by controlling the potential. One of the many ways in which corrosion can be delayed by changing the environment.